So someone asked me a while ago about parameterizations, and being that they come up all over the place and have a ton of different uses, I didn't know where to start this video. So I decided to go ahead and write out what I think, or how I think, about parameterizations. I don't know how this is going to go, but here we go. If someone asked you to draw a circle, how would you tell them to do it? No compasses are allowed. So mathematically, you could say a lot of different things. You could give the simple but gritty definition that a circle is the set of points that are equidistant from a center point, but then someone might ask you what you mean by distance. To be clear, I'm just talking about plain vanilla Euclidean distance, and what you probably first think of when I say circle. In order to avoid this ambiguity, you might also give out an equation of the form x squared plus y squared equals r squared. But something is a bit off here too. Sure, x squared plus y squared equals r squared is a totally valid equation for a circle of some radius r, but your instructions make the process of drawing the circle a bit more convoluted than with other graphs, as not all choices of x and y will yield a value that lives in the real plane. And you are not drawing the complex numbers in this example. We just want a plain vanilla circle. This is where parameterizations are helpful. A parameterization is, in its most abstract sense, just a set of functions where all the functions in your set are governed by independent variables, which are called parameters. Being that the parameters are the independent variables, it's nice to think of them as the controllers of our functions, which is generally how you would think of, normal Cartesian graphs, which are the most basic example of how I'm talking about parameterizations. That is, there is one element in the set of functions and there is one element in the set of parameters. So, for instance, a line, y equals mx plus b, where m and b are constants, as a parameterization has a function y and a parameter x. This example, along with other polynomials, form the most familiar and straightforward cases. But parameterizations in this general sense don't have to fit into our Cartesian function or polynomial mold. For instance, something more exotic like an elliptic curve, y squared equals x cubed plus ax plus b, where a and b are constants, can also be thought of as a parameterization, with one function, y squared, and a parameter x. However, the graphical interpretation would not be the elliptic curve one would expect. Rather, it would be a run-of-the-mill cubic function, sans the square term. However, if you wanted that famous symmetric geometric image of an elliptic curve, you could take the square root of both sides, and then move the plus or minus to say that our parameterization has two functions, y and negative y, and only one parameter, x. Graphing these two functions as x changes yields the desired geometric curve. Giving instructions to draw a circle with a parameterization is kind of similar to the different versions of an elliptic curve that we can get with parameterizations, or this general view of parameterizations, or just my thoughts on parameterizations. Anyway, getting what you naturally imagine, whatever that means, all comes down to how you want to visualize the information you're given in the parameterization. With the elliptic curve example, in the first case of the visualization, we only had one function, y squared, and we measured its value on an axis of the same name, y squared, and we let our parameter have an axis too. In the second rendition, we just took the graphs of each function and then laid them over each other, or just put them on the same coordinate grid. These two slightly different takes on just one equation via the lens of parameterizations gave us two kind of different visualizations. And we can make similar choices with the circle. There's just one hiccup. The radius is a constant for a circle, so under our general idea of parameterization, if we graphed like we did with an elliptic curve and we just left the left-hand side alone, we would have one function and a constant parameter of the radius. So the graph would just be a point on the line. With a bit of trig, however, you can make a parameterization that is a bit more meaningful. Recognizing that the Pythagorean theorem is a thing in the version of r squared cosine squared of t plus r squared sine squared of t is just equal to r squared, one can make a parameterization of two functions and one parameter, where x is just r cosine of t and y is r sine of t. When graphically representing this, when we ignore visualizing our parameter t and just focus on the xy points in the plane for our given values of t, we will have our desired circle, the plain vanilla Euclidean geometry one that you're used to. But we also could think of this three-dimensionally and keep track of the value of our parameter t that we put in and yield a helix as well. And being this general about parameterizations, it's really up to you what image you get out. And that's most of my thoughts on parameterizations at the moment. I don't like to think of them as producing one singular graph because that has misled me many a time. So anyway, parameterizations can be more complicated mathematical objects than functions are. Parameterizations are incredibly useful in places like calculus, differential geometry, and topology. In calculus and differential geometry, we use an arc length parameterization to arrive at certain geometric properties of curves, like a curve's arc length or a surface's curvature. And topological objects, like the real projective plane, can be parameterized to generate visual aids and a geometric framework for studying more local properties of these objects, connecting things in topology back to areas of differential geometry, depending on the way you're viewing them. Anyhow, thanks for bearing with me on this little dive into my brain. This is all I have for you today. I hope you enjoyed this video. As always, if you enjoyed it, give it a thumbs up and subscribe for more mathematics videos. As always, I am Nathan, this is Chuck, and I will see you next time.